Hello, it's Dr. Daystorms, and now we're in the third part of Chapter 8, and this is where we really start to get some of the nuts and bolts on how to draw the covalent bonds in these molecules, and this is where the stereotypical pictures of the way that you've seen things drawn probably in the past, where it comes from. We derive these from something called a Lewis structure, and then later we're going to talk about formal charges and what that means. So a Lewis structure is just a way to represent all the molecules with all of the electrons, those that are bonding, those that are not bonding. And let's first just do a Lewis structure. Actually, I'd like to first do a Lewis structure of just what that means. The way that you draw, let's do sodium. The way that you draw the Lewis structure for sodium is you always write down the chemical symbol, and then you use dots to display the number of valence electron that atom would have. So sodium is in the first column of the periodic table, so it would just have one dot. Let's do carbon. Carbon, we'd put a C, but carbon has 4 valence electrons. So we'd have 1, 2, 3, 4. Now let's do fluorine. How many valence electrons does fluorine have? First, let's just draw fluorine's chemical symbol, which is F, not Fl. It's F. Fluorine is a halogen. It's in group 7A. So therefore, it has 7 outer electrons. 1, 2, 3, 4, 5, 6, 7. So now let's look what happens when we start to have bonding that occurs. So we have a hydrogen, it has 1, and it's going to bond to another hydrogen, because remember it's a diatomic element. When these start to come together to form a bond, you're going to have 2 hydrogens. Notice now I use a dash instead of a dot. Each dash symbolizes 2 electrons. It would be the same thing as if I had written it out this way. It's just quicker and easier to do the dash. So this is the correct way. Okay? Now, hydrogen, remember, it follows the duet rule. It likes to have a total of 2 electrons. Whereas, carbon, nitrogen, oxygen, fluorine, they all like to have 8 outer electrons. So what about, let's do fluorine, for example. Remember, fluorine is F2 in nature. It's a covalent bond. Each fluorine has 7. Here, I'll do them in different colors. That way we can keep them keep track of them. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Whoops, that 7th one didn't come out right very well. Okay, when these two come together to form F2, it's going to look like this. We have 6 lone electrons on that colored fluorine. We're going to have 6 lone electrons on this color of fluorine, because we have 7 and 7 makes 14, but so far we've only used 12. 6 and 6 is 12. The other 2 are going to be in that bond between there. And so now that's why if we now go back through and we count, let's count the lighter colored fluorine. There's 2, 4, 6, 8, including the 2 that it shares. Likewise, the other one would have 2, 4, 6, 8. Okay, so Lewis structures represent all of those molecules. Remember, a dash means it's 2 electrons, and each dot represents a single electron. So we can look at both bonding and non-bonding, which a lot of times we call those non-bonding ones either lone electrons or lone pairs. So let's learn how to draw Lewis structures when we have 2 different atoms coming together. And you do need to know the rules and make sure you go in order. Alright? So let's do PCl3. The way to do this is first, you have to find the sum of all the valence electrons in all of the atoms in the molecule or polyatomic ion. So for phosphorus trichloride, the phosphorus has 5, because it's going to be it's in group 5A of the periodic table, and each chlorine has 7. So 5 plus 21 makes 26 total electrons. Now, if this was an anion, remember that means it has extra electrons, you'd have to add that number in. I'll show you an example later on. If it's a cation, it means it has lost electrons, and so you're going to have to subtract that number for every positive charge. Okay, so we've done that. So now let's say, how do we know which atom goes in the middle? Other than hydrogen can never be in the middle because it can only make one bond. Other than hydrogen, the central atom is the least electronegative atom. So here we would have the phosphorus in the middle. So then what you do is, this has already been done for us, but just to reiterate, we'd have the phosphorus and 3 chlorides. We know that the phosphorus has to make at least one bond to every single chloride. So we've used 2, 4, 6, so we have 26 minus 6. There are 20 electrons that are left over. So step 3, you want to fill in the octets of everything that requires an octet. Okay? And so, in this instance, these were the 6 electrons that we had already used up. Now we add 6 more to each of the chlorine, so that way each chlorine has an octet. So, we go from 20 that we had left over, minus 18, because we use 18 more, and there's 2 electrons left. Now if you notice, we have 2 electrons left, but phosphorus here, it's only at 6 electrons. It does not have 8. So the 4th rule is you fill the octet of the central atom with lone electrons. Lo and behold, there were 2 left over. Lo and behold, there were 2 of them left over from before. We just had to add 2 electrons here to phosphorus. Now phosphorus has 2, 4, 6, 8. So phosphorus is happy. The chlorine, I'll use a different color for chlorine. Each chlorine, let's use this bottom one, has 2, 4, 6, 8 as well. So it's happy. So that's what phosphorus trichloride looks like. But what happens, let's do a different example. Let's do HCN, which hydrogen cyanide. All right. I want to start this one. We have HCN, and we need to draw the Lewis structure for it. First off, let's figure out how many lone electrons each atom has. Not lone electrons, how many valence electrons that each atom has that's contributing to this molecule. Hydrogen's in group 1A, so it has 1. Carbon has 4, because it's in group 4A, and nitrogen has 5. So 1 plus 4 plus 5 is 10. That's how many electrons we're starting off with. Now, hydrogen cannot be the central atom, so now we're just comparing carbon and nitrogen. Which of these is less electronegativity? Or another way to think of it is which one is further away from fluorine? That's carbon. So carbon is going to be the central atom. Whoops, that is a really pathetic nitrogen. There we go. Now we know, I'm going to change colors here. We know that the carbon must make at least one bond to each of these. So we've used up 4 electrons. So there are 6 electrons left over. Now we have to go through and fill in the octet for the nitrogen. Well, nitrogen right now only has 2 electrons, because it's the 2 that they're sharing with carbon. So therefore, let's go ahead, let's see what happens if we put in 1, 2, 3, 4, 5, 6. 6 minus 6 is 0. So now we're out of electrons. Uh-oh. Look at this carbon. This carbon is not happy. Why is carbon not happy? It's not happy because it only has 4 valence electrons, or 4 electrons around it instead of 8. It's got 2 there and 2 between the carbon and the nitrogen, so that's only 4. So something is wrong. So what happens is if you run out of electrons before you have filled up all your octets, this is where you're going to be making double and triple bonds. Okay, so what happens instead is these 2 electrons can actually go to form another bond between the carbon and the nitrogen. So let's go ahead and let's do that. So let's just move those 2 electrons here. Now carbon's got 6, nitrogen still has 8. See, let's count the ones on nitrogen. We have 1, 2, 3, 4, 5, 6, 7, 8. But carbon still only has 6. So what we can do is let's take these 2 lone electrons and turn them into a dash to make another bond, to make a triple bond between the carbon and the nitrogen. So let's go ahead and do that. Let me erase those 2, and they now become a triple bond. We still have, let's count our total number of electrons. Okay, we have 2 there, and hydrogen's happy. Hydrogen likes 2, so that's 2, 4, 6, 8. So it's 8 around the carbon, 9, 10. We've used up all of our electrons, and that nitrogen as well. Here, let me show you the nitrogen in a different color. Also has 1, 2, 3, 4, 5, 6, 7, 8. So it's happy as well. So if I want to write this out, the Lewis structure would look for hydrogen cyanide. Looks like that. Okay, so if you run out of electrons before the central atom has an octet, you form multiple bonds until it does have the octet. Finally, we have to do what's called formal charges. Okay, and before we go over this slide, I want to show you something, and I'm going to try to let's just draw it out and see what we mean. We're going to do carbon dioxide. So remember carbon dioxide, which is less electronegative, carbon or oxygen? And the answer is carbon. So that means there's going to be an oxygen and an oxygen. Let's also figure out the total number of electrons that's in carbon dioxide. Carbon has 4 because it's in group 4A. Each oxygen has 6, so there's 2 times 6. So we're going to be using 16 electrons. We know the carbon has to make 2 bonds to oxygen. Alright? Now, let's go through and see how we can fill up. It is using 4. So we have 12 electrons left. Okay? So, let's say we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So each oxygen now has, minus 12, so we've run out of electrons. Each oxygen has 8 around it. So let's see how it has 8. So if we just look at the one on the right, let me change the color. Make it easier to tell. We have 1, 2, 3, 4, 5, 6, 7, 8. However, the carbon's unhappy because the carbon only has 2, 4 around it. Okay, so we now know that we're going to do something else. So what can happen instead let's take these two, bring them down to form another bond. And if we do that, the carbon has 6. We could go ahead and take these two and have it form another bond, so there's a triple bond. Okay? And if we do that, now every atom has 8 electrons around it. But there's another way that we could do this molecule as well. If we go back to the white here, let me use a different color. If we go back to this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now, instead, let's take these 2 electrons to make a double bond. And let's take these 2 electrons to make a double bond. So now we have a double bond on each side. Let's see what that looks like. Each atom now has 8 electrons once again. So which one of these is right? One way to tell is we want to figure out what's called the formal charge. Okay? So I'm going to redraw these 2 possibilities. On one possibility, we had it was looking like this for carbon dioxide. 4, 5, 7, 8. The other possibility looked something like this. So now this comes down to this idea called formal charges. Because if you ever think about it, we have already been doing some formal charges when we talk about ions. Like nitrate, it was negatively charged. That means one of the, at least overall, there has to be a -1 charge. Okay, or we had ammonium, which was a +1 charge. That means one of the atoms inside ammonium had to have a +1 charge. So formal charges is actually quite easy. The way to find the formal charge of an atom is you take the number of valence electrons that the atom came into the relationship having, and you subtract out the number of electrons it owns when drawn out in the Lewis structure in the molecule. And so what do I mean by that? Let's look at each of these. Okay, because whenever we say electrons that it owns, or whenever I'm saying that, for example, that oxygen owns each lone electron, but it only owns 1/2 of the electrons in a bond between it and the carbon. Okay, so let's just do an actual experiment. Not experiment, but let's just do the actual, one of these actual, for practice. So first off, let's write down the number of valence electrons for each of the atoms. I'm going to do the one on the right-hand side first. Valence electrons for each oxygen coming in was 6, because oxygen is in group 6A and the carbon is 4. Okay, the same thing is true over on the left-hand side. 6, 4, and 6. Now we want to subtract out the number of electrons that each thing owns. And so let's look first off at this oxygen. It owns 4 lone electrons, and it owns 1 electron from that bond, 1 electron from that bond. So it's 1, 2, 3, 4, 5, 6. So it owns 6. So 6 minus 6 is 0. Now let's look at the carbon. The carbon owns, and let me change the color. It owns 1 electron from each of the bonds. 1, 2, 3, 4. So when we take 4 minus 4, it's 0. And the oxygen on the right-hand side is the same as, I can try and change the color, but it owns 1, 2, 3, 4 lone electrons, and then 5, 6, because 1 from each thing. 6 minus 6 is 0. So everything is neutral on the molecule on the left-hand side. Now if we look at the Lewis structure on the right-hand side, we do the same thing. I'm actually going to start with the carbon, because the carbon owns 1 electron from each bond. 1, 2, 3, 4. So once again, it owns 4, so it's neutral, so that's fine. Let's look at the oxygen that's on the left-hand side of that molecule, and I'll do it in this color. It owns 1 electron from the bond with carbon, so that's 1, 2, 3, 4, 5, 6, 7. So it's 6 minus 7. So it has a formal charge of -1. So a lot of times the way that I would draw it is just with the minus sign. And I would usually put a circle around it so you can tell that it's negatively charged. Some people like to write -1. That's fine as well. Now if it had a 2 minus charge, you would have to write 2 minus. Now let's look at the oxygen on the right-hand side. It owns 1 electron from each bond with the carbon, so it's 1, 2, 3, 4, and 5. Six minus 5 is a +1. So it's got a positive charge. So, which of these two Lewis structures is correct? The better Lewis structure is the one that has the fewest number of charges. So, in this instance, the better Lewis structure is the one that we had here on the left-hand side. So I'm going to redraw it so that way we can see what it is. And it was this one. Whoops, I forgot to put the bonds in. That wouldn't be good. That's what carbon dioxide looks like. Okay, so let's go back. So with every Lewis structure that you do, you need to start to look at and to determine the formal charges. And the way to do that is you first count the number of electrons in lone pairs and half of the numbers of electrons that it shares in a bond with another atom. You subtract that number from the valence electrons for that atom that it brought in, and the difference is the formal charge. And so that's what we've been doing throughout here so far. So that's why when we did it with the 2 double bonds, the formal charge on every atom was 0. When we did it with a triple bond and a single bond, we have 1 oxygen that has a -1, 1 oxygen that has a +1 charge. So when we write Lewis structures, the best Lewis structure is going to be the one with the fewest charges, and it's also be the one that puts a negative charge on the most electronegative atom. And so if we look at the 3 possibilities here with C and O, we'd find that the best one, whoops, let me go back, hit the wrong thing. The best one is this one, the third one, because what are the formal charges? This is an anion overall, but what are the formal charges on these? If we look here, nitrogen is in group 5, but it owns 2, 4, 6, 7. That means that nitrogen has a 2 minus charge. The carbon has 4 bonds, and it's from group 4, so it's neutral. The oxygen, it's in group 6, but it only owns 2, 3, 4, 5. So it would have a +1 charge. That's not good. And if you notice, -2 plus a +1 makes a -1 overall. If we look at the one in the middle, and I'll do a different color for it. The nitrogen group 5, but it has 1, 2, 3, 4 lone electrons, 5, 6. 5 minus 6 is negative 1. So the nitrogen's got a negative 1 charge. The carbon, once again, was neutral. And the oxygen is 1, 2, 3, 4, 5, 6. So it's 6 minus 6, so it's neutral. But see, now we put a negative charge on the nitrogen, but oxygen is the most electronegative atom between those three. So if we look at this last one, let me use a different color, and let's figure out the formal charges on it. Nitrogen's in group 5. How many electrons does it own? It has 2 lone electrons, plus it makes 3 bonds, so that's 5. 2 plus 3 is 5, so it's neutral. The carbon's 4 minus 4, so it's also neutral. But the oxygen's in group 6. It has 6 lone electrons, plus it makes 1 bond, so it's 7. Gives it a negative 1 charge, and oxygen is the most electronegative of those atoms. And so therefore, it's the one that should have the overall negative charge. So that's why the third Lewis structure is the best of those three. I can't stress this enough that you need to practice writing Lewis structures, because you're going to see these throughout general chemistry, throughout organic chemistry, biochemistry, so they're very important. Just practice, 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 and if you have any questions, come to office hours, come to the help session, and I'll see you in class.